So my talk tonight will be on solar system bits. So that's everything in the solar system basically that's not a moon, it's not a planet, and it's not the sun. So everything else that there is, so there's asteroids, meteorites, dwarf planets, comets, and we'll talk about the Kuiper Belt and the Oort cloud and a few other things as well as we go along. Now to get an idea of scale, if we take the Earth and we reduce it 30 million times, we get a ball about this size. So the Earth is about 30 million times bigger than that. Now I've got a few models of some of the asteroids and that I'll be showing you, and they're at the same scale as what this is. I'll move it around so Australia's at the front because you might as well. Right, Australia's right there. Right, so if we reduce the Earth down by about 30 million times, it's about that size. The Moon, at the same scale, is this big. So you can see how much smaller it is. The best way to judge the size of the Moon is if I put this in front of Australia, you see it's pretty much the same size. So the Moon is approximately the same size as what Australia is. So when you look up at the sky, which at the moment you see a little bit of blur, you don't actually see the Moon. But if you look up, caught it, maybe? Right, stay. So if you look up on a clear night and you see a full moon, that distance from one side of the moon to the other is about the same as from Sydney to Perth. That gives you an idea of just how far away it is. Now back in ancient times, of course people used to watch very carefully at the heavens, and they noticed that there were some stars that moved relative to all the others. Of course they wouldn't see these move like this. Each day they would look and they would see it would be in a slightly different position. All the other stars would all be in the same position, and certain stars would gradually move. And they'd move across the sky and they'd get to a certain spot, and then they'd go backwards, and then they'd go back forwards again. They would do this loop. That's what they turned these stars planets, which means a wandering star, because these stars wandered through the heavens with all the other stars that seemed to be fixed and stayed in the same position. And other than these stars that just wandered through the sky, everything else was predictable. You could always tell which direction the sun was going to come up. You could tell that the sun was going to go down. You would see the moon, it would get bigger, and then it would gradually get smaller, and then it would disappear, and it would come back again. It was all predictable. So they could use the setting of the sun to build calendars, like Stonehenge here, so that at particular times of the year, the sun would set between two particular places, and they knew that at that point the sun would start to come back the other way, and the weather would warm up, or it would be the end of summer, and the days would start to cool down. So it was all predictable. They could build calendars. They could build other things that could help them predict the seasons as well. This is the Temple of the Sun in Mexico. This is the largest pyramid in the world. If you go to this, and I've been there, it is huge. But unlike the pyramid that they have in Egypt, which is huge stone blocks, these are actually built just of a whole pile of stones and then finished off to give the smoother looking edges. But by volume it is much, much bigger than the Pyramid of Cheops in Egypt. Very impressive. And they use that to also predict the seasons, that the sun would set or rise in certain locations. There are other pyramids built at the site, and they could tell what time of the year it was by where the sun set relative to all the other pyramids and other buildings that they had at that particular site. So for thousands and thousands of years we had basically the classic solar system. We had the sun and the moon, and we had the planets that were visible to the naked eye, and that was it. That's all it was in the heavens. It was all predictable, and it was like that for thousands and thousands of years. And then on the first day, in 1801, the 1st of January, it all changed. Giuseppe Piazzi found a new planet with a telescope. It wasn't visible to the naked eye. He found the first planet in many, many thousands of years. The astronomers had sort of figured that there seemed to be something missing anyway. Because back in the early 1700s, a guy called Mr. Bode published this law. And if you put the planet number into this equation, so you go 1, 2, 3, 4, 5, you get a fixed series of numbers, what they call Bode's law. And if you put the distances to the known planets into this thing, you get the distance that this formula predicts in terms of the Earth's distance. So this predicts that Mercury is at 0.4 of the Earth distance. It's actually 0.39. So you can see the percentage error is actually quite small. And there was something missing when you put this number here into the equation. There should be something at around about 2.8 times the Earth's distance. And there wasn't. There was Mars, and then there was Jupiter, and there was this gap in the middle. And when they could calculate the distance to Ceres, and they put it in here, and you could see it's only just barely 1% out from where this law predicted where it would be. Now, it might be a law, but it actually has no basis. It's just a mathematical curiosity. It has no basis as to why it should be correct at all. It just happens that the planets sit relatively close to these distances that are actually measured versus what they predict. So it's not a real law. It just happens that it fits, and it fits quite well. But if we put in Uranus and Neptune, we find that it actually predicts the distance for for Uranus quite well, and Neptune it's out by almost 30%. So it doesn't hold up very well once we get out to there. But if we put the distance of Pluto in this formula, again it happens to actually fit quite well. There's no reason why it should, but it's just an interesting mathematical curiosity that the distance to the planets actually fit very, very closely to this law, which has no meaning. So as a result, they discovered Ceres, and Ceres was called a planet, which made Ceres very happy, I'm sure. But when they noticed how dim Ceres was, but it's still relatively close, it's much closer than Jupiter, they realised it must be quite small. And we now know that compared to the Earth, that's how big Ceres is. You can see it's very small. It would actually stretch from about Melbourne to Sydney in size, which is still a very big rock, but for a planet, it's quite small. And then over the years, as they got better telescopes and they kept looking, they found more and more of these new planets, and they kept calling them another planet, another planet. So Pallas was a planet, Juno was a planet, Vesta was a planet, Astrea was a planet, Hebe was a planet, and they had all these planets that they kept discovering. But when they measured the distances, they found that they were all very, very close to the same distance. They weren't close to one another, they were scattered all around the solar system, but they were very close to the same distance from the sun. And they just found more and more. You can see they started to get fairly small, only 100 kilometres or so, some of them. So they just found more and more of these. And after 50 years, they'd found so many of these, they decided that they needed to do something. So that's when they created the term asteroid, and poor old Ceres lost out. It was no longer a planet. Ceres was demoted to become an asteroid, which didn't make Ceres very happy. Now there's so many of them out there, they think there's between 1 and 2 million asteroids that are bigger than a kilometre across. So there's millions of them that are a rock a kilometre or more from one end to the other. But because they're so far out from the sun, the average distance between each one is about 1 million kilometres. That's about 3 times as far as from the Earth to the Moon. That's how close these little rocks are. So they're a long way apart. So unlike on the movies, you don't go through the asteroid belt and have asteroids and meteorites everywhere. They go to a lot of trouble to get a spacecraft to fly past one. They've had a number of craft that have flown through there, basically blindly, and they haven't hit anything. They had no idea whether they were going to hit something, but they just sailed right on through, didn't hit a thing. Now, most of you have probably heard of the asteroid belt, and that's between Mars and Jupiter. All these little white dots here represent asteroids in the asteroid belt, and you can see they come from fairly close to Mars all the way out almost to Jupiter's orbit. And there are millions and millions of them. So see, between 1 and 2 million, greater than a kilometre, hundreds of millions in total. The Galileo probe, on its way to Jupiter a number of years ago, they actually flew past an asteroid called Gaspra. That was the first one. They had to navigate very carefully so they could come close enough that they could actually take pictures of it. And this was the sequence. As it got closer and closer, you could see Gaspra getting bigger and bigger until it sailed past. And they calculated that Gaspra is a rock, it's about 18 kilometres long, and it rotates every 7 hours. So you have this rock that's nearly 20 kilometres across that's spinning in space every 7 hours. You can see it's got a couple of impact craters on it as well. It's covered in a lot of dust. There's a few smaller impact craters. So that was the first one that they actually sent a spacecraft past to take a picture of. They've sent a number of probes since then. There's Gaspra. These are 4 of the others. Ida is actually interesting because it has a moon. So it's an asteroid that has a moon that orbits it. They think what's happened at some time, something's hit Ida and knocked a chip off the corner, and that chip has just stayed in orbit around this asteroid. They call that one Dactyl. It's only about 1 kilometre across. It's basically, it's just a little chip. It got hit one day and the little piece of rock is still spinning around.
So there's enough pull on Ida to...
Yeah, just to keep it in. It's going very, very slowly because, like, if you were to stand on any of these, particularly even these larger ones, like this one and this one, you could jump into space because the escape velocity, like on the Earth, is very, very fast. You've got to go many thousands of miles per hour. But to get off the surface of one of these, just jump and you're in space. So yeah, there's very, very weak gravitation, but this little rock is just enough that it just keeps it there orbiting. This one here, Itokawa, you can see it's actually quite small. These are not to scale. This is only half a kilometre across. So these are many times bigger. So this is actually quite small, and you can see it's got little rocks and stones on it. And they think what this is actually 2 rocks, which you can see there, and the gravity is just holding them together. And then all this dust has just sort of come in from space and it's just stuck there. Little rocks have landed on it. So if you were to actually hit this with something big enough, it would just break in two and the dust would scatter everywhere.